So today we will be discussing about cascading full adders. Okay, yesterday we had seen adders and subtractors, right? So wherein we looked at different circuitries and we looked at different truth tables and how they are getting generated and how we can actually generate equations from the truth table and consequently your logical circuitry. Fine. So today we will take this full ladder and then we will try to cascade them and we will try to make them we'll put them into task, okay, and we will see how best we can use them for further enhancements. Okay. So using two half adders, a full ladder can be implemented. I think you all are very much aware of this, and an n-bit adder can be built by cascading, or we can say that we can connect these adders in series, right? Okay. Each full adder represents a bit position. The least significant bit can be a half adder because a carry from the less significant position does not exist. Right? So what we are trying to say here is initially there wouldn't be any carry. Later on, the carry gets generated. Each carry out from a full adder becomes the carry in to the next higher stage, right? Okay. So whenever a carry gets generated in the first stage, okay, now look at this diagram here. I have actually cascaded a full adder. Okay. So this is a 4-bit full adder. How do I say it's 4-bit? Because I have x0, x1, x2, x3. Okay. Consequently, it gets added with y2, y3, y1, y0. Okay, so x0, y0, that is one. x1, y1, that's another set. x2, y2, that is the next stage. Then x3, y3 is the final stage. So since I'm using 4 full adders, it becomes a 4-stage, 4-bit adder. Okay, so this is my carry in. FA is nothing but your full adder. S0 is your sum for x0 and y0. The parameters which gets added is the full adder and the sum comes out. Then your carry out is here. Okay, so the carry out which comes here in the first stage is actually the input to the second stage, C in, okay, which is nothing but your carry in. The first stage we do not have any carry in, okay, as consequently when we get 1, 1, okay, that is when it gets generated. Okay, so a carry gets generated and then it needs to go to the next stage, and then next stage. So due to this, what is happening is there is going to be a lot of delay for the propagation of carry. Okay, so we will see what can be done in order to get this rectified. Okay, so students, do you have any doubts in this diagram here? Any doubts here in this diagram?
So one doubt I had.
Yes, yes.
Sir, in the first adder, sir, the S1 adder, the CI which is being given as input, will that be the same as C0?
Yes, exactly. Both are the same. That's why I told the output of first stage, okay, is the input to the second stage. So which means both are just connected with a line. That's it.
No, sir, the next C0. Like in the same adder, the other C0.
No. See, this is local. Okay, I understood your question sign. So just like how we used for mux, inside I had I0, I1, I2, I3, but externally I was using A, B, C, D, right? So this one is carry in, carry out of this local full adder. Understood? So once this comes out, this will actually get in to the next stage full adder. Okay, so it doesn't mean that in order to get this confusion rectified, okay, how we can do is maybe we can write it as stage 1, okay, stage 2, stage 3, stage 4. Okay, so in that way there won't be any confusion, like CO1, okay, then CI1, then CO2. Understood? Then
yes,
CI2. So like that, no? If we write stage wise, then there won't be any confusion. Okay.
Yes,
I hope you understood this, right? Okay. So any confusions here? Can I proceed? Can I proceed?
Yes, sir.
Fine. So this box that you see here, okay, this box is nothing but your full adder. Okay. So what is your full adder? If we go back, okay, so this whole thing, okay, this whole thing is actually inside the box. Okay, this whole thing is inside the box. So I have just put, the terminals inside, the terminals, which is X, Y, C in some carry out. But here internally we have all these logic gates, right? So similarly, this is represented as a box. Okay, it's just represented as a box. Then I have my inputs C in some carry out. Okay. But internally, we actually have a lot of logical circuits enabled. Okay. So it is with stage 1, 2, 3, 4, 4 stages. Okay. But there is one downside. Okay, for this full adder, there is one downside. The carry needs to be propagated from one adder to the other. So till the carry comes, this adder will have to wait. The second stage adder will have to wait, because we never know what is going to be the output of C naught in first stage. And this is actually waiting for the carry from the first stage. So second stage is dependent on first stage, right? Because it's all connected in series. So series means it is like a chain, right? So it is like a connecting link. If one link breaks off, then we cannot call it as a series chain. Isn't it, students? Correct? Okay. So similarly, so what we have to do here is we have to see that, this carry getting actually passed on to the other sections needs to be faster. So which means my second stage, let's say, this is my third stage, full adder carry should not be dependent on some other carry. Okay. So we developed something called look ahead carry generator. Okay, look ahead carry generator. So we will see that in some time. Okay. The add time required is determined by calculating the propagation delays to the full adder. So because of which, what is happening? There is going to be a lot of delay. By the time I get my C out, it's going to be a lot of delay. Remember, students, every transistor, okay, will actually add up to the delay. Okay, every wire that you add can add up to the delay. Every millimeter increase in wire can actually increase the delay of propagation. Okay, so if we have so many wires, okay, then what is going to happen? There is going to be a lot of delay. If my wire is too big, too large, then what is going to happen? There is going to be increased resistance and increased capacitance, right? So here in this stage, what's happening? I have my stage 1 carry, and I have to wait, till I get my C out. I have to wait for it to pass stage to stage, and you can imagine as to how many gates are involved in each stage, right? So if each single wire's millimeter increase can change resistance and capacitance, think about the transistors, think about the gates, think about the wires needed for connecting them, right? So it's a complex thing that happens when data passes from one end to the other. Okay, fine. The carry propagate from one full adder to the next higher order full adder. This type of addition is called ripple carry propagation. Now I think all of you are aware of the word called ripple, right? Where have we come across this kind of word, ripple? Yes, can someone unmute and respond?
So ripple factor.
Sorry, I didn't get you there.
So ripple factor in physics we had studied +2.
Okay, normally you have seen something called ripples. Maybe when you were a child, you would have seen when you throw a stone and on a water body, right? What happens? There is ripples that gets, caused, right? So similarly, why it is ripple? Because it's like a circle which moves from one point to another point, right? So similarly here, your carry is getting generated from one stage, moving to the next stage and the next stage and to the final stage, right? So it is like a ripple effect, okay, that is seen on the surface of water. Okay. Total delay time is the product of sum of the number of stages in the adder. So as I told you, delay is very much dependent on all the stages. As the number of stages increases, the number of transistors, the number of logical gates, the number of wires has increased, and thereby enabling increased delay time. So when I say increased delay time, say for example, I have given input at 5 nanoseconds and I'm expecting an output, okay, in another 5 nanoseconds. Okay, so which means at 10 nanoseconds, my input, whatever I have given here, okay, should be propagated stage after stage, and I should be able to get it here in the form of C out and S3, right? But if that doesn't happen within the specified time, then it means that there is violation, okay, there is propagation delay, all those stuff, right? Number of stages in adder and carry in carry out propagation delay time. The carry into carry out propagation delay is used instead of input to some output delay, because it is the signal that ripples from one full adder to the other. That is what we have discussed, right? So as the signals pass from one stage to another stage, what is happening? There is a delay associated. So there can be chances that the output is not coming at the exact time. So in order to solve this problem, okay, in order to get this problem solved, what we did was we are looking at something called carry look ahead generator. Okay, sometimes it's also called look ahead carry generator. Okay, so in this case, what we are doing is we have a generator here which actually generates the carry. Okay, which generates and propagates a carry beforehand. And what happens here is in the previous one, it had to wait for the previous stages, okay, all the connected previous stages for this C out to be computed. But here what is going to happen? We are going to generate, okay, based on the XOR gate. So you can see here, okay, this is done by generating all the individual carry terms needed by full adder in few levels of logic as possible. Okay, so as much as possible, what we will do is we will generate few values, and then we will try to propagate them. Okay, those values which we already know that is going to happen, so we will generate it. So this is a well-known equation for us, which is the sum equation for full adder. A is XORed with B and XORed with C. Here I've used X, Y, and C in. Okay, so the same equation is used. Fine. So this is your block diagram of carry look ahead adder. Okay, so X, Y, XORed, and C, your C out. Okay, so that is also given. Then I get a total sum. So we will see now exclusively how this carry look ahead logic works out. Okay. Now this is the circuit of your full adder, right? Let me take A, B, and C, right? So A XOR B, okay, then C is given here. So A XOR B XOR C is nothing but my sum, and my carry should be AB, BC, CA. So AB is taken from here. Okay, next next your C is here, right? And that is again multiplied, and I have A XORed with B, which means A bar B, right, plus B bar A. So that is XORed and given here. The final ORing, okay, that happens is nothing but your carry. Okay, A, B, B, C, C. Now, there are two important new terms here. Okay, one is nothing but your PI and GI. So we have not seen these terms previously. So this is nothing but your propagate and generate. PI means propagate, GI means generate. So what are they propagating and what are they generating? They are just propagating and generating the carry terms. Okay, so A is XORed with B. So instead of having the full equation like that, what I will do is I will represent it as PI. Okay. Then A and B are multiplied with each other. So instead of calling it AB, I will call it as GI. Okay. Now, one thing that you all should understand is GI will be high only when A and B is high. Okay. Because this is an AND gate. So in AND gate, what is the values? If one of the inputs are low, then the total output is going to be low. So which means A and B should be high for my GI to be 1 or logic high. Similarly, with your PI, okay, the XOR operation is happening, and accordingly, okay, based on your truth table, you will get high values, right? So PI is nothing but your A XORed with B, and GI is nothing but AI into BI. So that is your AND gate. Fine. So what we will do now is we will actually call SI. Okay, SI is nothing but PI plus XORed with CI. Right. So your SI, the final sum, is nothing but PI is coming here. What is PI here now? PI is nothing but your AI is XORed with BI, right? So PI is here. Then this CI is getting XORed here, right? So the final SI, instead of calling it A XOR B XOR C, I'm just calling it as PI XORed with CI because PI is A XORed with B. Is it clear, students? Any doubts here? So far, any doubts? Any doubts, you can ask me. Is it clear? Can we proceed? Okay, fine. Thank you for that confirmation. So instead of calling it A XORed with B and then XORed with C, I will just substitute A XORed with B is nothing but my PI. So that is my propagate. Similarly, my CI, okay, CI plus 1, okay, that is the next stage. So in the next stage, what is happening? This is nothing but my GI. GI is here, okay, plus PI into CI, okay, PI into CI. What is this PI? PI is coming from here. So PI is here, CI is here, and then that is getting added with GI. Okay. So now we get started with our multiple stage. Now remember, whenever a question is asked with regards to carry look ahead adder, these two equations are very much important. Okay. In order to know these two equations, you will have to draw this diagram. Okay. Fine. So in order to draw this diagram, you will have to know how a full adder is. So what is the equation for full adder? So if you know that equation, then it's very easy for you guys to bring this circuit up. Okay. So G is called a carry generate and it produces output. Okay, fine. Yeah, we have seen this. Now, this I is like a stage. Stage 1, stage 2, stage 3, as I told you, right? So let us take I as 1. So if I substitute I as 1, what is going to happen? 1 plus 1 is 2, right? Then G1 plus P1, C1, right? So this is my second stage carry. Okay. Similarly, C3 is equal to C3. Okay. So which means I am going with the next stage 2 plus 1. Okay. So C3. So wherever I is there, you have to substitute 2 plus P2, C2, right? Now from the previous equation, we have the value of C2, right? C2 is here. what will I do? I will put this equation as it is here, G2 plus P2, and C2 I will substitute in the bracket, right? So in my next stage, what I'm going to do? I'm going to do a normal algebra. Just going to multiply P2 G1 plus P2 P1 C1. Okay. Now, if you observe here carefully, okay, if you observe here carefully, C3 is not at all dependent on your previous stage carry, right? What is your previous stage? C2. C3 is not at all dependent on your C2, right? We have only C1. We have only C1, right? Now let us go with the next stage, C4, which means I'm going to increase the value of I. So C4 is equal to G3 plus P3 into C3. So I have the value of C3 here, right? So G3 plus P3 into C3. C3's value is put up here. Now G3 plus P3, G2 plus P2, then C2's value I have here. Again, I multiply with C2 value here. Students, you're able to understand, right, how we are getting it? Or do you want me to annotate? Is it clear?
Can you annotate it once?
Yes, yes. Fine. So here, let's take C3. Okay, C3 is G2 plus P2 into C2. So this C2, okay, C2, I will substitute this equation. Okay, this whole equation. So what happens here? G2 plus P2. So this G1 and P1, okay, this G1 and P1 is actually coming here. Is that clear? Till that point, is it clear? Fine. Is it clear till there?
Yes, sir.
Okay. Next comes your general multiplication with this. Normal multiplication. Just a normal algebra. Okay. So I have my final C3 equation here. So this is my final C3 equation. Okay. Next, what I'm going to do is I'm going to take the help of C3 here. How am I going to take the help of C3? C4 is equal to G3 plus P3 C3. Fine. So G3 comes as it is here. Okay. So G3 is coming here as it is. Okay. Then I have P3 also coming here as it is. Okay. Now C3 is water. This whole thing will come here. Okay. So which means indirectly it comes here. First, what I will take is I will take this equation. G2, P2, C2. So this equation, I will put it there directly. I'm bringing it here. Is that clear, Sayan?
Yes, sir.
Because I'm substituting for C3 here, right? And C3
yes,
equation, I have it here, right? So now I need an abbreviated form of this. I need an abbreviated form of this. So what will I do? I will take the previous equation, which I've put in red rectangular box, right? So G3 is coming here as it is. P3 is also coming here as it is. G2 is coming here. Okay. Then P2 into C2. Now what I will do is I will take the help of C2's equation. What is C2 equation? I will go back here. Okay. So G1 is here. Okay. Then P2 into P1 C1. Is that clear? And then
yes,
in this,
sir.
and in this step, it's going to be a normal, algebraic multiplication. That's it. So ultimately here, what you have to remember is the main thing here is this equation. Okay, Si, your sum and your carry, this equation. And then once you have this equation, doing this is very easy. C2, C3, C4. It's very easy, just that you have to take the help of the previous equation. Now observe, okay, in your C4, to get your C4, it is not at all dependent on C2 and C3. You just have only C1 here, right? So here also you have C1, and in C3 also you have C1. In C2 also you have C1. So it is dependent only on C1, right? So what is going to happen here? Let's come back to the diagram. Even this stage is dependent on only one first carry. This stage is also dependent on this carry. The stage is also dependent on this carry. So once this gets generated, once the Cout gets generated, parallelly I can get S1, S2, S3 parallelly gets executed. Anyway, S0 will come along with C0, right? As soon as this comes, okay, as soon as this comes, what is going to happen is immediately this value gets comes and sits here. As soon as I get this value, all these three stages will automatically get generated. Now, students, are you getting it? Is it clear? With this one, what was the disadvantage? Using this, what was the disadvantage? It had to wait for stage after stage. But here, no matter whatever stage it is, I am trying to put the equation in such a way that it depends only on my C1, the first stage carry. Okay, so in that way, I am actually cutting time and not waiting for C2, C3, all this. Okay, I'm just waiting only for the first carry to get generated. Once that carry gets generated, then I will be using the same thing. So I hope it's clear, right, students? Yes, can I have some response? Okay, thank you. So how do we get this circuit? Just from these equations. Let's take C2, G1 plus P into C1. So I need an OR gate, I need an AND gate to get this executed. So I have D1, G1, C1. So I have an AND gate, OR gate, C2 comes in. Similarly, your C3 is equal to G2 plus P2 into C2. So instead of me directly putting it, what I will do is I will take the expanded form, okay, the final equation, and I will try to bring it here. So I need P2, G2, okay, and P1. So all that is taken here, P2, G1, G2, okay, and C1. So all that is taken and given C3 and C4. This is how we obtain it. Any confusions here? How we have got this logical diagram, students? Can I proceed now? Yeah. Okay. Fine. So this is about your carry look ahead adder. And sometimes what is going to happen? Yeah. So that is what I have written a note here. Note that C4 does not have to wait for C3 and C2 to propagate. In fact, C4, this is a very important point. Okay, so you should make note of this. C4 is propagated at the same time as C2 and C3. Right? So that was the time-saving thing that we did with your look ahead carry generator. So typically, this is how an IC is actually generated or IC is manufactured, and this is how it is inside. Okay, I will have all these inputs. Okay, A, B, C. A first stage, second stage, third stage, and fourth stage. Okay, so A1, B1, A2, B2, A3, B3, A4, B4. So all my inputs here. And for my propagation, I will use an XOR gate, and for my generate, I will use an AND gate, the same as we saw in our adder circuit. Okay, for propagation, we are using an XOR gate, and for generation, we are using a AND gate. So the same, this circuit is actually put up here. Okay, so P4 and G4. So using this, using my inputs, my P4, G4 gets generated. So using my P4 and my C4, okay, what is going to happen? I can actually generate my sum. Okay, P3 C3 sum 3, P2 C2 sum 2, P1 C1 is my sum 1. So this is how we actually have for your carry look ahead adder. So main thing what you have to do here is you have to mention this diagram. Most important thing is mentioning this diagram, and these two equations are very important, your propagation and generation. Okay, and then you can also mention this with this equations only. It's becoming easy for you to calculate C2, C3, C4, or even C5 as well, right? Only thing is the equations keeps on building up, and it's dependent only on C1. The beauty here is that, you know, it's dependent only on C1. Okay, so that's the best part of it. And this circuit can be implemented using any logic, as I've mentioned, as we have seen or learned in the previous classes. It can be either only in the NAND gate, or it can be done in NOR gate implementation, or we can also use this AND or logic. That is the normal logical implementation. Okay, so this is about your carry look ahead adder. Fine. So the next thing that we will be seeing is your binary comparators. So what is a comparator? Can someone tell me? The word itself has its meaning, right? What's a comparator? What's a comparator?
Like checking for greater than and lesser than or equal
exactly, to. Exactly. So I'm trying to see if it's higher than or equal to or less than. Okay. So here also we can use binary values for the same. So binary magnitude comparator is a circuit that provides output information indicating the magnitude of two input operands or operandi. There can be three output conditions: equal, less, and greater. Okay, so that's what I have depicted here in my truth table. So 2-bit combination, normal thing 00011011, right? Here, how am I getting A is equal to B? Because both A and B are 0. So A and B is A equal to B is 1. It's not greater than B. It's not less than B. So 0, 0. So similarly, now A is 0 and B is 1. So who is greater? A or B? Which is greater? B is greater, right? So I can say that your A is less than B. Thus 2 becomes 0. Then in the next case, A is higher than B because A is 1 and B is 0. So in that case, A is greater than B. This will be high. The other two will be 0. Next, for 1, 1 also, it's the same case as 0, 0. So here it is not worried about high value or low value. It is only comparing if A and B have the same or not. Okay. So that's about your binary comparator and about the truth table. Now, using the truth table, what's going to happen? We can generate equations. Okay. Of course, as I told you, greater and less than is actually checking for low and high values. Equal to is just checking if both are having the same values. Okay. Fine. Now, once I have this truth table generated, it's easy for me to get the equation, right? So wherever I have 1, those are my outputs. So 1 is at A bar B bar plus AB, right? So that's nothing but your XNOR. Then for greater than B, you have A B bar, and for less than B, it's corresponding to A bar B. Any confusions here, students? Till here? Is it fine? So the same logical implementation can be done with these equations. Okay. So XNOR, directly I get my A is equal to B. Then for A greater than B, it should be A multiplied with B bar. So A I will take here, and that will be multiplied with B bar. So this gives my A greater than B. For less than B, also I can make the use of an inverter and AND gate. Now this is for my 2 bits, okay, just 1 bit A and B. So suppose I increase this to a higher size, okay. So suppose I make it 2 bits. So in that case, A1, A0, and then B1, B0, right? So this will be considered. So using my K-map, I can actually put those values, okay? First generate the truth table, get this. Once I generate the truth table, I can easily get this equations. Size when it's increased for 2 bits, okay? So what is going to happen? You will have A1, A0, B1, B0, right? Here we had just A and B. So again, A I'm splitting into 2, B I'm splitting into 2, right? So I make it 2 bits, and we get a truth table. Okay, so once we get a truth table, for your practice, what you can do is you can actually create a truth table, and once it's created, you can put those values into K-map, okay, and individually verify if actually these equations are correct or not. Okay, so that's for your practice. So I have put it up here, okay, for your reference, where you will have these values here. So A1, A0, okay, so all zeros, so A is equal to B. So let's see one case where A is less than B. So this is treated, this whole thing is treated as B. Okay, it is not treated as B1, B0. You're getting it right? This whole thing is treated as B. And this whole thing is treated as A. Okay, so A will have 2 bits and B will have 2 bits. So it's a 2-bit comparison that happens. Fine. So A is compared here. So A is 0 and B is 1. So which means A is less than B. Right. So let us take one more case where A is greater. Yeah. So this case where A is greater, A is 1 and B is 0. So A is greater than B. So as I was mentioning, right, you can extend this for your 2-bit comparison. Okay. And so once you have extended this for your 2-bit comparison, you can create a truth table. You can see wherever the values are high, and accordingly you can get an equation. Okay, so those equations will be these, okay, your min-term equations. And once you have this min-term equation, it's easy for you to create a K-map. So once you have the K-map created, for your practice, okay, what I have done is I have not solved the K-map here. Okay, I have not solved the K-map. So I want you to put up K-maps, okay, and fill in these values inside K-map and check if these values are correct or not. Okay, so just you can take this as your homework, as your assignments, okay, and check if these values are correct or not. So I will get certain equations. So based on those equations, I'm going to implement my logical circuitry, just like how I had implemented the circuit for these above equations, right? So this is about your comparator, right? So maybe in the next class, we will look into the code converters, okay, as to how you would have seen this BCD to X3, right? So similarly, this can be seen, or